Hello, cpponsea. How are we doing? Yeah, that's what I like. That's what I like to hear. All right, thank you so much for choosing to come here today to learn about SWAR, which is SIMD within a register. So I get the impression that if you've come to this talk, you're interested in performance. And I guess the first question to answer is, since we're talking about SIMD, is what is SIMD? I guess if you've come to this talk, you might have some context. But if I can get any hands up, anyone who might be able to tell me what is SIMD, what it stands for, or yes? Single instruction, multiple data. That's exactly right. So what you might be more familiar with, if you haven't heard of SIMD, is what you call SISD, which is single instruction, single data. You have two integers that come in, you do a single instruction on them, you get one single integer back out. And with SIMD, you can take in, let's say, 4 integers, two pairs of 4 integers at a time, add them all together with one add operation, and you get 4 results out at the same time. And what you may have heard before is people saying that SIMD requires special hardware. It requires AVX or Neon or whatever it may be. And have you guys heard that before? That SIMD requires specialized hardware. Hands up if you guys are pretty convinced that SIMD requires specialized hardware like SIMD or. Okay, by the end of this talk, I want to have convinced you that that is not the case. You do not require specialized SIMD hardware to do SIMD. If you take nothing else from this talk, you don't need specialized hardware to benefit from SIMD. And furthermore, the techniques I'm going to show you are the cheapest way that you could do any form of parallelism or kind of SIMDification. So that feels like a bold claim, and you're like, what is this guy talking about? Of course you require, you need specialized hardware to do SIMD. Yeah, we'll see how that goes. So I think also further to motivate this talk, we as developers are going to need to continue to think wider, to think more about how we can parallelize our algorithms in the context of CUDA or doing hardware SIMD, and hopefully, as we'll see, software SIMD. We're going to need to kind of think wider. How can we parallelize these algorithms more effectively? AI is coming. The acronym that shall not be named. I think I'm the first person I've heard to mention AI in a talk so far. I think we've avoided that so far. But in CUDA and in AI applications, you kind of have to do a lot of things all at once. So hopefully by the end of this talk, you'll start to feel more comfortable thinking about how to generalize doing parallel computations. So yeah, by the end of this talk, what is SWAR? And hopefully you'll be able to feel comfortable implementing your own SWAR functions and benefiting from it. So very quickly, who am I? Who is this guy who's talking about doing SIMD without SIMD hardware? My name is Jamie. I am a developer at a music startup called mayk.it. We're based in Los Angeles. I've written lots and lots of C++ code for our audio engine. We use Traction Engine that Dave Rowland, who's here, maintains, which is great stuff. I've written a bunch of the neural inference code or contribute to that we use at Make, and written a bunch of other languages. I went to Queen Mary, where I did the Sound and Music Computing course and got a BA from the London College of Music. And just a bit of housekeeping, just a big thanks to my friends Eduardo Madrid and Scott Bruce, who contributed massively to this presentation and helped me get a lot of these ideas and helped me learn about this stuff. So a big thanks to them, because they helped very much contribute to the success of it. If there's any success of this from this presentation, it's very much due to them. Okay, so I've talked about this. So what is SWAR? How can you do SWAR, SIMD within a register? I've said that you can do SIMD in general purpose registers. So hopefully this slide isn't too confusing. I've written these integers in a binary representation. So you've got 1 and 2 and 3, and you add 1 and 2 and you get 3. And if you drop this into your editor, I promise that static assert comes out as true. Not confusing so far? Okay. So here's where we get a bit SWAR-y to begin with. What we can do is you can just pretend. Just pretend there's lanes. Just imagine, oh, hey, the first 4 bits are gonna be one lane, and then you start again. It's a different lane. And you can see here, and this is why I've done it in binary, so you can see this imaginary lane. You've got a pair of 1s, a pair of 2s, you add them together, the carries all work out, and in the bottom row, you get a pair of 3s in the different lanes. Does that make sense? So I remember where I was the first time my friend Scott Bruce explained this to me. And he was like, we were just chatting at this tiki bar and, just shooting shit and just say, what have you been up to? What have you been working on? And he says, oh yeah, I've been working on this software SIMD library and we're, just using general purpose registers to do SIMD. And I was like, well, what are you talking about? And he says, yeah, you just use general purpose registers and you just pretend that you have lanes. And I was like, what? You can do that? Turns out you can do that. And just, yes, to be very clear, what's happening here is you see we have all these lanes, but it's just one 64-bit add, and you can see that this is, interpreted differently. It's 4,000 something plus 8,000 something equals 13,000 something. But you interpret this result differently, and it's pretty much a SIMD operation. Does that make sense? Okay, so the elephant in the room. Can anyone notice or point out what could go wrong with this? Carries. Okay, exactly. You can get overflow. If we had a full lane, we had a 15 here, something bad's going to happen, right? You're going to overflow, and then you're going to spoil all the more significant lanes than the one you're in. Exactly right. So, damn, is it game over for SIMD within a register? Well, turns out no. You can do a handful of bitwise operations to kind of prevent lane crossing, and that's the core of what makes SIMD successful. Because you could be doing 4 simultaneous operations, and then you do a handful of bitwise operations to prevent the lane crossing, and you end up with tremendous savings in terms of the amount of computation that you do. So you can see that I think the headline here is that, say if you did you had a 64-bit register and you had 8-bit wise lanes, so you had 8 bytes in that register. If you did it in the SWAR way, you'll do 1 addition and 1 store, and you'll do 8 additions in total, if you consider it in the SWAR way. But if you did that scalar, you're going to do 8 additions and 8 stores. So in terms of the number of total operations, that's 2 operations versus 16 operations. And then you'll do some overhead of the bitwise operations, but they're so cheap that it's pretty minimal. So hopefully that makes sense on why these techniques can be so powerful. So I've been talking about these techniques in general, but I want to show off that this is, in fact, a library that we've made. And this is how you use it. You can create a SWAR instantiation, and you tell the SWAR template how many lanes you want, what's the underlying type you want to use. And so for this example, you've got 8 lanes in a 64-bit underlying type. And this is exactly the same as we've done before. I've written it in hex because it's nice to see. It can be nice to, when you've got bytes, it can be nice to write in hex. But you can see, you've got 1 plus 1 is 2, 2 plus 2 is 4, 4 plus 4 is 8, and it's in hex, so 8 plus 8 is 10, but 10 is obviously 16. Yeah, so that makes sense. Any questions about this so far? Yes?
Yeah, so you're using a 64-byte internal type.
Yes.
But the 8 bytes, how do you know what the maps of this? What are you adding? Are you adding like cars inside cars?
No, so there are no cars actually present here. So so effectively they're cars. So because you've got 8 bits, and so each one of these lanes is effectively a car, and then you could reinterpret that or cast that back out to some array of cars if that's what you wanted, or like to move it back into some string, and we'll see a little bit about that later on. But yeah, this is just pretending that they're cars basically. And if if you drop this static assert into your editor, this will be, that's what comes out. And if you want to look at the library, that's the link for it there, the cpponsea/zoo on GitHub. So just kind of going back again and talking about the different ways that you can do parallelization. So hopefully this doesn't look too complicated or too unfamiliar. If you want to square an array of numbers, you can go and square each of those values individually. If you want to do it using ARM neon intrinsics, you can do it that way, and you can do 4 at a time, and then process the stuff at the end. Are you guys familiar with SIMD? This looks okay? All right. And then in the SWAR way, this is what you can do. You load in to your SWAR register the values, and you can use these, a lot of the functions we've written in the library that will give you the results. So you can see here, each one of the lanes has been squared because we're doing the multiplication on the same value. And this is the multiplication unsafe value. And this won't take into account the lane crossing. Maybe if you have, and we have the safe multiplication, and we'll see how to, we'll show you right in this talk how you can do lane safe operations. But say, for example, you knew that your data wasn't going to come anywhere close to the boundaries of the type. You can say, hey, I want to make the savings. I don't want to do those bitwise operations. So it's all kind of down to you and how you want to write your application. So I've said that we can we're going to write some SWAR code and understand that. So we're just going to talk about equality. So imagine we have 2 SWARs, and we're going to lane by lane compare the values and say, are any of these equal? And if any of them are equal, we'll return like a Boolean true for any of the lanes that were equal. So I think this is where, if you can pay attention, this is where you might need to pay attention the most. This is where I'm going to need to pay attention the most to explain this. So if you have 2 values, normally you just do equals equals if you had a scalar value, and that's fine. But there is no intrinsic that's going to give you this result. So we need to implement this ourselves using bitwise operations. So we have 2 values, we've got them, and then the first thing we can do is if we exclusive all those values together, any of the lanes that were exactly the same will have a 0 in them, because we've exclusive ordered them. Any of the lanes that were exactly the same in either of these SWARs will be 0. So that's kind of where our journey starts. We've exclusive ordered these values, and we have a 0 lane. And we go, OK, now we've got this 0 lane. All our job is now is to identify that 0 lane and return some kind of Boolean representation of that's where the equality was. So far, so good. We just need to return to the caller that is the lane with the equality. So this is where we need to be aware of the lanes. So hopefully what you can see is if we subtract 1 from each of the lanes, so each of the lanes we subtract 1, we'll borrow from the lane above, but then we're going to borrow from the lane above, and if we subtract 1 from this value, it's going to turn that most significant bit off, but we're going to disrupt the lane above it. So this is where we need to have an awareness of not messing with the other lanes. So what we can do is we can get this most significant bit constant, and we're going to OR that in with the value we had before. So that means no matter what, we're going to turn all of the most significant bits on. And then what we can do is we can get our 1s, and we can kind of subtract that from all of them. And that means necessarily that we're going to, so you see in what was the null channel, we're going to have that most significant bit as 0, and everything else is going to be 1s. And we go, OK, great. So that most significant bit is now a 0. That's cool. That identifies where the nulls are. But you can see in the lane next to it, we've got this kind of false positive. So we need to account for this false positive. And so what we can do is we'll flip these over, we'll invert it. And what we'll do is we'll AND it with our initial value, because before it was a 0. And that means that when we've finished that calculation, we'll have the most significant bit of the lane that had the 0 will be on. And that's how you represent a Boolean in this SWAR way. The most significant bit of the lane being on represents the truthiness of that lane. So what we can do is we can jump into the Godbolt and we can implement this and see what this is like. So basically what we've done here is we've just copy-pasted all of the headers of the zoo library into this Godbolt. The zoo library is headers only, so it's really easy to get started with and to drop into your project. So this is our implementation. This is everything we did, the equals operation. So a little larger? Oh, thanks. I'm just going to move that over. OK, can we all see that? OK, great. So as we can see, we do the XOR of the input. And then with the XOR value, we OR in the MSB, so all of the most significant bits of each lane are definitely on. We subtract 1 from each of those lanes. So now the most significant bit of the 0 lanes is 0 with some false positives. So we'll invert that. We'll turn all of the most significant bits on for the nulls and the false positives. And then we'll get rid of the false positives by ANDing with our initial value. And then we basically blit out the values which aren't the most significant bits. So that gives it to us in the Boolean SWAR representation. Hopefully that makes sense. And we can have a look at some of these tests we've written. So for this value, this is in hex, so the 80 value, that is represents the char that is the most significant bit on, so it's like 1 and then followed by 7 zeros. Hopefully that makes sense. So this is the concisest way of I felt like I could write this test. We have some primitives that let you write SWARs with kind of like literal values, so it's a little bit more user-friendly. And if we get time at the end, I can show you that. But hopefully you can see here, 1 and 1 are the same, 2 and 2 is the same, so that's like that.
Jimmy, why don't you use an example that is not the same?
Yes, and we've got one right here. So this one, these are not exactly the same. This 1 and 5 are different. And you can see that that is not the same. And we can even, let's make this a different value. And then we're going to get the compiler mad at us. And it's not going to compile because the static assert is mad. But we can take this out and make that, so that should be a false value, and then it will be happy again. Hopefully that makes sense. All right, let's head back over to slides, but it's having a moment. OK. All right. Do we need to refresh the page? Maybe. OK. All right. So any questions about that? Make sense? All right, fantastic. So that's a kind of introduction to the Boolean SWAR concept. We represent the truthiness with the most significant bit of the lane being on. And what we'll touch on later on is this idea of a pseudo Boolean SWAR, where maybe you only care about the fact that there's the least significant bit, the least significant truthy value, and there's anything later on you don't care. So for example, string comparison, we'll talk about in a bit. You only care that there is a true in the least significant bit because you found the null terminator. Anything beyond that, you don't care. You found that true. So we'll talk about that a bit later on. The SWAR library is general purpose. Hopefully you can see that this is very configurable. The kind of generic programming paradigm has been applied here very heavily. So you can have SIMD with like total freedom. You can have any size of lane that you want. You can have any underlying type that you want. You don't even have to have power of 2 lanes. You want lanes of 5 or 7, some other random prime number? Like, why not? Who cares? And what's really powerful is that you can create operations on the types that you want. For example, like a pop count. There's not really a SIMD implementation of that, but we've implemented that in the library. So you can have that on your SWAR types. And what's cool is like casting back to the underlying type is 0 cost. And furthermore, there is 0 cost to loading, compared to hardware SIMD, there's this whole cost of loading into the AVX registers and going back out. Here, there's no cost. There's no cost to loading in and out of the AVX registers. So that's something that's really cool. So what we're hoping for with the SWAR library is to even transcend and go beyond just doing software SIMD. We're hoping that this is also going to be a generalization for doing SIMD in software, in hardware, combinations, and hopefully we'll be able to generalize to CUDA and GPUs, and so you can translate all of this, all of your work that you've done for these parallel algorithms to any width and any platform that you're interested in. So what can you do with this? So Eduardo, who's here, and who's really started this project, he was using set operations and SWAR, which he presented in CPP 2019 for a project he called Pokerbotic, which is a project that is a very fast implementation of evaluating poker hands. And if you're interested in set operations and how they can be done very efficiently using SWAR, then I definitely recommend you check out that talk. And furthermore, Eduardo and our friend Scott Bruce implemented a very, very fast Robinhood hash table implementation. And they presented that at cppcon 22. So if you're interested in the implementation details of using SWAR at kind of in a production strength application, then that is the place that you'd want to check that out. So some benchmarks we've talked about. That this SWAR stuff is cool and it's supposedly going to be performant. So what I'd like to point out is, so we've got the we're going to talk about string length, and these are for string length. These are benchmarks going over, a randomly generated corpus of strings, primey flavored lengths of strings, and all that sort of thing. So for glibc, this benchmark I was running on this computer, by the way. So glibc, their neon implementation of string length, it takes, I think it was like 5,000 nanoseconds to go over the whole string length corpus. And so that was this one here. And then our Zoo portable implementation that doesn't use any hardware SIMD comes in at just a little bit slower to do the whole benchmark corpus. It's about 5,500 nanoseconds. And we have 2 different flavors of that, and they have very similar performance. But yeah, neither of these use any hardware SIMD. This glibc Neon uses hardware SIMD. The glibc portable implementation that is only C++, vanilla C++, is significantly slower. And if we get time at the end, we'll have a look through that implementation, because there's lots of unnecessary places where there are control dependencies as opposed to data dependencies. And I think our hypothesis about why that implementation isn't that effective is because it's putting a lot of pressure on the branch predictor in an unnecessary way. And then what's really fun is you look at the Zoo Neon implementation, where we compose the SWAR techniques and doing that with real hardware SIMD. That's where you get the best performance, because we're doing SWARs within 64-bit registers, and then we're doing 4 of those at a time using hardware SIMD, and that gives the performance that beats the handcrafted assembler of the glibc implementation running on this computer. And yeah, so the Zoo Neon runs in like 70% of the time of the glibc Neon handcrafted assembler. And I think that's really exciting because you can look through the glibc neon assembler and it's not that fun and very difficult to understand. And the zoo neon implementation, you can read it and it's reasonably plain free to read if you're comfortable looking at a few intrinsics. So why is this library and why are these benchmarks so good? You might be asking, that's kind of some cuckoo bananas implementation. The cuckoo bananas benchmark, sorry. And so it's going to get a little, I don't want to say philosophical, but something like that. So I'm sure, I don't want to generalize too much, but I'm sure we've all met managers or people who work adjacent to tech who kind of understand developing, going a bit like this. You know, the more lines of code you have, the more time you put into a project, the more people into a project, the more your project is able to kind of do stuff. It's kind of this linear relationship of inputs and outputs. You add more people, the project gets more productive or whatever. If you worked in tech to any degree, you'll probably recognize that it generally feels a little bit more like this, where the more lines of code you have, the slower and the more ineffective each line of code can get. Do you guys resonate with that experience? That can be the case. So if you guys were in, I guess most of you saw Dave Abraham's talk about when he was talking about Alexander Stepanov and generic programming and being able to compose knowledge into source code and have that source code compose. I think a lot of that influence we've kind of taken into our library here. And using generic programming and having your source code and your knowledge compose, you're able to kind of get results that look more like this. So that's just like a little digression, but hopefully that explains a little bit about the philosophy and the reason why we think this library has been successful. Okay, so I said I'd talk about string length, and we're going to have a look at the string length implementation that you can do using SWAR. So what is string length? How does string length work? Basically, you have a char pointer, and you just need to scan along until you find the null terminator, and what is the distance between the initial pointer you've got and the null terminator, and that's the length of the string. And so a naive implementation might look a little bit like this. You just count until you get to the null terminator, and then just return that count. And that's fine. That might suit your needs. But we want to do this in SWAR. We want to have the best implementation we can. We'll have the fastest implementation. So how do you do that? So really the only complicated thing that you need to have an awareness of is that we're going to need to do an aligned load because we're going to be reading speculatively into memory. We don't want to read any invalid memory. And we want to be aware of if we've read any memory that is not strictly our input, we want to just account for that. The aligned read will guarantee that we're not going to read, that the data we've got is going to be on the same page as our input. So that's why we need to do an aligned load. Then, basically, we need to just figure out, once we've loaded in some bytes, which one of these are empty. And if any of them are empty, we should do the math to calculate how long that string was so far. And if it wasn't empty, then just keep going, keep loading bytes, keep consuming bytes until we find that null, and then do that math to figure out how long that string is. So we've got one more Godbolt. Okay, so that's a little bit off to the side. Okay, so, all right. So this is our string length implementation. We've got our little helper functions here. We've got our MSBs and our ones, which hopefully we're familiar with at this point. We've got a type alias and that sort of thing at the top as well. The number of bytes per iteration, that's going to be 8 because, or no, it's not going to be 8, sorry. It's going to be 64 because that's how wide our type is. We're consuming 8 times the number of lanes. This is a little helper function which is going to help us calculate the length of the string. And this is where we do our aligned load. If we get time at the end, we'll kind of come back and have another look at that. But basically, all we need to know now is, have we got any empty bytes in the SWAR we've just loaded? OK, right. Where were we? OK, we want to see if there's any empty bytes. If there are empty bytes, then we do this little bit of maths to figure out how long the string was all in. And if there wasn't empty bytes, then we haven't reached the end of the string, and we just need to advance and repeat. So that leaves the question. How do you find the empty byte? So we can come up to this function here. And this is really the kind of the core of this implementation. So we spoke a little bit earlier about the Boolean SWAR and finding nulls. And so what we could do exactly the same as we did before. We could do this equals operation. And that will tell us exactly how many nulls, we can do an equals operation with all nulls and this. So that would give us the right answer. However, we don't care about any of the nulls that happen further up than the first one, because it's not the end of the string. We've already found that one. We only care about the least significant null, because that's the one that represents the end of the string, and we're going to literally ignore the rest of that when we're calculating the solution. So we can have a slightly laxer finding of nulls. We can technically only find the first null, and as long as we do that correctly, then it's fine. So this is why this function is called find first empty lane. In most cases, it will find all of the lanes correctly, but there are certain inputs where it will have false positives for more significant lanes. And this shaves off, if that is the requirements you need, this will shave off a handful of assembly instructions. And that may be useful to you. So when you compare these functions directly, you'll find that there's maybe 2 instructions different. They're generally about 7 or 8 assembly instructions for a function like this. And there's maybe two instructions different. And when you're really trying to push the frontiers of performance, then that can be the thing that makes all the difference. So how does this function work, and why is it different to the one we've already looked at? So the main difference is, if you remember from before, we were ORing in the most significant bits, and that was the thing that was preventing the lane crossing. That was the safety mechanism we were adding in. In this example, we're just going to go ahead straight away and subtract the ones, because if there is a null, it's going to borrow from the lane above, and that borrowing from the lane above can cause issues more significant than we are. But we don't care, because we only care about the least significant 0. So that means, from this line, we are going to necessarily, if there isn't a 0 in any of our lanes, we subtract a 1, we're going to switch on the most significant bit of the lane, which was a null. And that's the thing that we're going to use to identify that lane. And then, so basically, we just need to convert that now into a Boolean SWAR. So now any of the lanes which had a null have now their most significant bit on. If we invert our initial input bytes, the lanes which had a null will now have their most significant bit also on. If we AND those together, that means that in this variable, only the lanes which had a null will have their most significant bit on. And now, all we need to do is just basically split out any of the bits we don't care about, which are just anything that's not the most significant bit, because that's what a Boolean SWAR is, and this will give us our answer. And that's how you determine what is the first empty lane in this SWAR doing it in the SWAR way, with that looser consideration. So you can see how it's doing effectively the same thing, but we are removing some of the lane safety because it's not required for this specific application. And this is an insight that our friend Scott Bruce came up with, because he was thinking about it and he was like, well, we don't need strict equality there. We only care about the first one. And he was like, well, maybe there's some optimizations we can make there, and this is more or less the implementation he ended up coming up with. So that was a really cool thing. And then so then you'll do this little bit of maths. You'll get the aligned base, and you'll get the index of the first true lane, the first true byte from the least significant direction, and subtract the pointer, and that will give you the length of the string. So that's how you can do string length in a SWAR-y way. And it's not, I hope you'll agree, it's a little bit more complicated, but it's not untenably complicated to think about doing operations in this way and thinking about it in parallel by default. And what's really exciting is that if you had a computer that had 128 bit registers by default, like doing this SWAR-y in that for that width of register, all you'd have to do is just do that, and then your parallelization is all of a sudden wider and just as correct. The way this generalizes is very...
That will compound. Just do underscore doing 128.
Right, there you go. So all of a sudden, you've got much wider... or maybe it's not happy with that. Maybe I've done something else wrong.
I think it does.
Oh, okay. Okay, maybe I need to include some other headers or something like that. You went underscore T. No, it's not happy with that yet. Okay, maybe it's maybe it's
Because it doesn't have
Je zet double lanes in de setting of.
Oh, I see. Yes, of course. Oh, I'll just remove that. That's fine. What have we got here? Yeah. Okay. Yes. Okay. Great. So yeah, in theory that should work. But if you want to do less, you could do a UN 32 underscore T, and that'll work out. That should compile just fine. Yeah. There we go. And it's not really that much assembly. This is pretty optimal. You just have one loop and you just keep going until you get that answer. There's just the one invariant, that one real control dependency, and that's it. There's no unnecessary control dependencies in that loop. Okay, so let's jump back over to the slides. Great. All right, so an interesting side note, when we were benchmarking the GCC stuff, benchmarking the string length functions, is I didn't have a Linux machine, so I beamed into some Linux machine on the cloud, just to run the benchmarks on x86 on Linux, just to kind of get a broad overview. And I'd put in this just as a reference. I didn't expect it to do well, but just what would it do? And this, I can't remember exactly what the values were, but this was smoking all of the implementations we had, this naive implementation. And I was like, wait, why is the compiler optimized that so well? That seems so unintuitive to me. We were Eduardo and I emailed Eduardo, and I was like, dude, you're not gonna believe, this is crazy. And he was like, I don't know how this is possible. And I was like, yeah, I don't know, this is nuts. It was maybe a factor of, I don't know, I can't remember, but it was faster than everything else. And so we started to go through the assembly, as you do on GCC. And what we found is that this is the assembly that came out, is that GCC had found the pattern that was string length. He was like, oh, I see what you're doing there. That's string length. Let me just drop in this implementation as opposed to trying to explicitly optimize exactly what you said. Here, I know what you're doing. I'll just make a call to this thing I know already. So that was interesting. Clang, it seems, will optimize what you've given it in the IR representation as opposed to making calls to things that it already knows. And that was that was really funny. Okay, so we're more or less getting to the end of the talk. I just put in this slide to show you that it's really easy to get going with the Zoo library. To get going, you can do a Git submodule or whatever you're doing, but the Zoo library is header only. Getting started with Zoo is super simple. So if you had a submodule, you just clone it in and just pound include and away you go. Doing the CMake, also super easy. There's just a handful of lines of code that you need. Okay, so to start wrapping up, SWAR is fun, SWAR is cool. I enjoy doing it. It's like puzzles, like doing the bitwise operations. It's kind of like for me, it kind of feels like a Sudoku. You want to do the safe bitwise operations and get this result. I don't know, I think it's really fun. I think it's a cool puzzle. And so so there's fun things you can do there. And furthermore, the library is co-evolving with the applications that we're making. So with the Pokerobotics stuff that Eduardo has done has improved the library. I think that was really where the library started, is with the Pokerobotics stuff. So that was what started the library, and then the library gets created, and then Eduardo and Scott were like, hey, we can do this hash table. And then that feeds back into the library, and the library gets improved, and then the library is improving the hash tables. And then it's this feedback loop of writing the applications, improving the library, writing the applications, improving the library, and one informing the other in a kind of positive cycle. We think that the way we've been able to use generic programming and kind of representing knowledge as source code is what helps us get effective results, and I think the way we've done generic programming lets the compiler just see through all the levels of abstraction and just generate more or less optimal results, which is more or less what we've seen. And hopefully this has been an invitation to think more about parallelization, think wider, and to start thinking about ways that you can implement things that will parallelize by default. So that's more or less the end of the talk. If you've got any questions or you'd like any clarifications, then I'd absolutely welcome those. So